All right, welcome everybody. Good morning. We are in the Z performance and capacity stream this morning. Uh, just a reminder that this and all sessions are being recorded. This presentation is going to be the latest IBM Z performance brief by Dave Hutton. If you have questions, please feel free to throw them into the chat. I'll monitor that and I'll get the questions to Dave so he can answer them along the way. And please don't forget to fill out your session feedback forms. So with all that said, please welcome Dave Hutton.
Hey, thanks, Donna. So yeah, good morning, good afternoon. Um, my name is David Hutton, and I presently do the LSPR alongside Gary King, who is still with IBM. And then, you know, upon rating the machine, there's also the onus that comes with that of having to um, handle critical situations whereby a client buys the machine and doesn't attain the advertised rating. So we get to mine their data and figure out what's different about how they're running than what we measured. So that's my current role and responsibility at this place, boiled way down. So yeah, we'll talk about this is the latest performance brief, which is now officially Z17 that we can talk about. Just announced a couple weeks ago. So yeah, I'll jump right into it. There's a lot of words, but I'll give you the short version. So primary performance drivers of Z17 relative to Z16. I've boldened the principal elements. The clock frequency of the processor runs at 5.5 gigahertz, which is up from 5.2 gigahertz, which is almost a 6% boost in clock frequency. So right there, that delivers about half of the total performance just from clock frequency alone. And clock frequency is one of these nice tides that lifts all boats. Unlike the other half that we attained from what we call microarchitectural enhancements, design changes intended to improve or increase the instructions per cycle, or if you take the inverse of that, the same will reduce the cycles per instruction. So what else have we done? A significant microarchitectural change since Z16 is instead of, well, we had 1-to-1 of these physical level 2s on a per core, and we had 8 physical cores per chip on Z16. We still have 8 physical cores per chip on Z17, so that's not changed. However, we do have 2 additional level 2s per chip. So that increases the total cache available. And I have some topological diagrams that'll show that a little more clearly, and we'll talk about why that change was made. But briefly for now, the bullet here calls out that we're operating in a smaller technology, so we can squeeze more transistors on the chip. So you'd think we go from 8 to 10 across the board, both cores and L2s, but turned out we needed the area of those 2 extra cores to make room for this data processing unit that's now on the chip, where we basically took the ASIC, the custom ASIC that we made for the I/O cards, and we brought it on to the processor chip. We'll talk more about why that was done. The second generation AIU, this is the artificial intelligence unit, which we have 1 per chip. The second generation, each individual one is faster than the first generation, significantly so. But the other cool thing is that before there was only the ability for the local chips or the local cores on the chip to use the local AIU. So, if you had a workload running on a handful of zips that was really beating up on its local AIU, there might be other chips that have local AIUs that are idle. Well, now we can distribute the work from the overloaded AIU to the other chips on the drawer that are less actively used, and so we can clear the queue much faster. Total processor count is now up to 208 from 200, which is plus 4%. It's a modest increment. But again, each one of those cores is, we'll see in a bit, it is effectively 11% more throughput in typical configurations. So this leads to, I don't want to get ahead of myself, but it allows the max box config to grow by about 15%. So a few brief words about the memory subsystem. I mean, a lot of this largely telegraphs from Z16. It's the second generation design with the redesigned distributed physical level 2 and the virtualized level 3 and level 4 caches. I'll recap those on a couple slides coming up. But the notable change is that the total physical memory supported on the box grows from 10 terabytes per drawer across 4 drawers on Z16 for 40 terabytes total, up to 16 terabytes per drawer on Z17, which is 64 terabytes total. So now this is also in tune with the max that that ZOS supports per image. So if you can have one massive partition per drawer at 16 terabytes, and if you had 4 of these partitions on the box, then each drawer based partition could, now realize the maximum supported bandwidth of ZOS partitions. I don't know too many clients that operate in that space, but I'd be remiss to call out that it is, if I didn't call out that it is technically possible now. The cross drawer penalty is substantially similar to Z16s. For those that are interested in this space, there's some details aside, but the general rule of thumb is from like Z13 through Z15, if you went cross drawer, it was about a 10% hit to do so. When we went to Z16 and we had to redesign the caches and then redesign the interconnects between those caches, that was one of the downsides of that new design. The cross drawer penalty got worse, so it's now about 20% worse. Z17 dialed it back a little bit. If you imagine a needle where Z15 was and where Z16 is, the Z17 needle is about 90% of the way towards Z16 versus Z15. So it crawled back maybe 10% of that distance, but for most intents and purposes, you might as well consider it very similar to Z16 in the cross drawer penalty regard. And then finally, Prism. Nothing too fundamentally different. The max box partition count is still 85 as it's been for quite a while now. And we tend not to talk too much about specifics of Prism algorithms, but suffice it to say that it's something we do on every generation. We look at the field and we look at configurations that were suboptimal. They usually tend to be corner cases if we do all this right. But nonetheless, if there's a way to improve those corner cases going forward without breaking the general case, that's the real trick. Then we work that into the base algorithms going forward, and we've done that for a couple of client experiences this time around. And this concept is still fairly new, called fair share of spares. Prior to Z16, like if you had a mixed configuration with like we described here, ZOS, Linux, and coupling, all the dark cores on the box would pretty much be carved out for the ZOS space almost exclusively. And the idea there would be you're giving them and Prism the maximum sandbox to optimally place ZOS partitions so that you can minimize cross-chip activity and certainly cross-drawer activity. everything you can do with dark cores to maximize and performance and reduce latency for ZOS partitions is the way it was done um, for thousands of years. However, over time, Linux, I think we've supported Linux for over 20 years now on the platform, and I hear numbers that say we actually sell more Linux MIPS than we do ZOS these days. And in recognition of that, we've changed that algorithm from being the dark core allocation algorithm from being very ZOS centric to fair share of spares, meaning if you have 10 ZOS engines and you have 10 Linux engines and you have 50 dark cores on the box, instead of giving 48 of them to ZOS, we'll now give 25 of them to ZOS and we'll give the other 25 to Linux. So we award the dark cores fairly according to the purchased engine count of the respective pools. And we do the same for coupling facility, just because it's easier to do it consistently for all the engine pools rather than make a special case to not do it for them. Yeah, that began on Z16 and it's continuing forward into Z17. So mixed mode Linux client should be very pleased with this. Okay, and this is the one slider. If you take away nothing else from this talk, really the first set of bullets is key here. Everybody wants a single number. Yeah, if you Google the Z17 LSPR, it'll bring you out to a page which has all the tables for Z17, and it's got the previous 3 generations of tables for Z16, 15, and 14. All the models, what the MIPS and MSUs are, and the low, average, and high LSPR ratings. Yeah, so you have all these curves that vary over the n-ways, blah, blah, blah. Everybody wants a single number. So I was like, well, okay. We look at, to come up with a single number, we look at what we have installed in the field, all the boxes that we have, and then we take the median of the 7 series. And that's right now, somewhere around a 12-way or a 14-way. And so we compare, the 12-way or the 14-way Z17 versus the same on Z16. And pound for pound, when you do that, you get an average of 11% more throughput per engine at that equal n-way. So that's the single number boiled down for marketing from all the LSPR curves. That's how we do it. The other 2 metrics there, max box capacity. So this is, okay, you take the 4-drawer max config Z16 versus the 4-drawer max config Z17. The total engines per drawer grew from 50 to 52, and then each one of those engines grew by about 11%. And this kicks you up to about a 15% total increase in box capacity at the maximum end. And yet another way to look at capacity is how the per drawer capacity looks from one generation to the next. And that we're saying is about a 20% difference. I have a table coming that shows how we determine that, but it's the same idea as the max. We look at the standard drawers, not the max drawer. That's the same as the above, which would be 15%. But the standard drawers grew by 20% because the typical engine count from Z16 was about 41, grew to 45, and again, each of those 4 engines is also bigger, and so that's how we get to 20. For those interested in subcapacity models, I'm sure you're probably very familiar with the table in the middle here. So we have the 400 series, 500 series, and 600 series subcaps. So the mult column is the multiplier, where the 7 series is the benchmark or the standard bearer of 1.0 for that particular generation. So yeah, the 600 series runs at about 2/3 the the effective clock frequency of the 7 series, while the 5 series runs at about 42%, and then the 4 series runs at about 12%, that of the 701. And we held these ratios pretty consistent from Z16 to Z17, so no surprises or churn there. And then also show the relative MIPS based on those the multipliers and what we know the full speed line to be. The subcap line is still limited to the number of GPs that would fit in a single standard drawer. And so for Z16, that was 39. Z17, that's up to 43 now. And then the final blurb at the bottom about SMT, this hasn't changed, since really since Z14, Z15. You have the option to turn on SMT2 on IFLs and zips. It's on by default on the SAPs. And there are 2 ways to look at SMT2 capacity. Either I'm on Z17 running single thread and I flip the switch to run on Z17 with SMT2, in which event I can expect each of my engines to gain about 10 to 40% additional throughput, where the average being about 25% additional throughput. The other way to look at it is I already have it on Z16 and I'm just going to Z17 and I intend to leave it on. When you do that, the average throughput just tends to track with the single thread, which we say at the very top of the page is 11%. So whether it's whatever it's running, whether it's 1 thread or 2 threads, the average improvement will be the same, about 11%. Okay. So I mentioned this briefly on my lead-in slide, this notion of a data processing unit. And you'll also hear Z17 referred to, at least the processor referred to as Telum2, given that the Z16 CPU was referred to as Telum. Is this the Z17 processor? And as I said, we relocated the FICON functionality from a custom chip that we designed and put on these PCI Express cards. We took that functionality and we just designed it into the processor silicon. So now we don't have to design 2 chips. We can, or rather, fabricate 2 chips. We can just fabricate 1 chip, and that's got everything on it. Now, why might we want to do this? Well, what this facilitates is, you can, today we have these 2-port FICONs and these single-port OSAs. And by putting these custom ASICs on the processor chip, it allows us to support, we can basically double that, where we can now support 4-port FICONs and 2-port Network Express. So, and if you can double the amount of support and you don't need the IO slots to the degree you did before, you have the potential to significantly reduce your IO slot quantity, which in turn has the potential to significantly reduce your IO drawer quantity, which, depending on how many IO drawers you do save, or if you only tipped 1 or 2 into another frame and you can reclaim those 2 drawers, there is a potential in some cases to eliminate an entire frame. So this obviously leads to physical power and performance per watt savings. So if you do nothing else, you have the potential to cut down on your footprint and your power consumption, which, as everybody is going greener these days and sometimes by mandate, this is a good thing. However, the play IBM really wants to make here is we're going all in on, I talked about the AIU, but now we're also building the AIU onto PCI Express cards as well, that are being bundled and aggressively packaged with Z17 deals, these Spire cards. So free up the IO space for Spire. And then in this way, if you have a Z16 that operates today, you can supplant it with a Z17 that has substantially more, capacity for AI processing, even generative AI, not just the predictive. Um, but you don't have to increase the Z16 footprint or power consumption in order to arrive at this, or to facilitate this increase in AI processing. So that's the idea, big picture. Um, and a recap, in case the when I talked about the difference in I think I call it the distributed physical level 2 cache design. Um, this is just I'm not going to spend too much time on this because this is a refresher coming from Z15 to Z16. But the graphs, they're the topological views at the right. The top one shows Z15, classic hierarchical view, memory above level 4 cache, which is shared by so many level 3s. And then each level 3 at the chip level is shared by so many CPUs under it. And you see the dashed line that denotes what we call the nest versus the cores, where the cores are the eggs in the nest. You think of it that way. Well, logically, conceptually, as a driver of the car, Z16 feels like it's organized the same way. You got memory level 4, so many level 3s to the level 4, and so many processors to the level 3. However, physically, it's a different animal altogether. Like I said, the upper right for Z15, the logical view and the physical view are the one and the same, but on Z16 they're different. So the logical view is the apparent, what it feels like to whoever's driving the car, but the physical view is what you would see when you open the hood, and you realize pretty quickly it doesn't look like anything that's come before or since. We have pretty much just cores, and then these level 2 caches that are paired or mated 1-to-1 with each of the cores. And then each of those level 2s on a chip, or they have this bi-directional bus that communicates between those 8 level 2s on the chip. And then the chips themselves are bonded in pairs, forming these DCMs. And then the unused level 2 space from each of the cores that is bonded with each of the level 2s facilitates the virtual level 3 at the chip level, and then the other chips in aggregate virtualize the drawer level 4 cache. And we do it all with just these physical level 2s that are mated 1-to-1 with each of the processor chips. The bottom left shows the single drawer view showed in the bottom middle, but fully populated, and it shows all the cross chip and DCM interconnects. And then the blue in the upper left just shows a single chip zoomed in with the olive, with the dark and light olive buses reflecting those bidirectional buses we talked about. Okay. Now, for Z16 versus Z17 specifically, I just, I'm sticking with the logical view because it keeps life simple. And it's effectively, again, what the end user would intuitively experience. So yeah, the red boxes denote on the right denote the processor chip. So you can see that they're I drew every other one, and I just have a very tall, skinny box alongside it as a placeholder for the second chip on the DCM, which is denoted by the gold box that surrounds a pair of red boxes. So that's the single drawer view again. You look down at Z17, it's the same view, conceptually. So then looking at the statistics and metrics on the left, we call out what's the difference between, what are the specific differences between Z16 and Z17. And again, like I kept the color coding consistent. So like, the red for the CP chip and the orange or the mustard for the DCM, that matches the color coding of the text for help with identification. And then I highlighted in green on the Z17 things that are bigger or faster or generally improved relative to the previous generation. So again, 5.2 gigahertz for the core, now 5.5. The level 2, each one was 32 megabytes. Now each one is 36 megabytes. The virtual level 3, we used to have, it's since there used to be 8 level 2s on the chip, and one of them is dedicated to the core as its physical level 2, at least primarily, then that leaves 7, the other 7 level 2s to serve as the virtual level 3. So that would be 7 times 32 megs to get 224 on Z16. Well, you do the same. We have 10 total, less the one that's dedicated is 9. And then instead of 32, they're all 36. So the level 3 went up significantly from 224 megabytes to 324 megabytes on the chip. And then extending that same math to the virtual level 4, instead of 8 chips times 32 megs times everybody but the owning chip, you had almost 1.75 gigabytes of shared virtual level 4 on the Z16 drawer, and now it's 10 times 36 times 7, and so now you have 2.52 gigabytes per drawer. So significant shared cache growth. And the topology is generally similar. Again, we still have 8 cores, but this time we have 10 level 2s, and it's otherwise quite similar. Another, just zooming in and another view. So on the left is a CP chip, with the CAD drawing of the actual circuits and what the silicon looks like. So the upper right core is our sample core. So his physically attached level 2 is dark purple for reference, and it's 36 megabytes. The other 9 on the chip are the virtual level 3 for this sample core. And the same is true of any core, that you would pick. And then here, this light blue box where I'm circling and there's this gap above it, this is the DPU, the data processing unit. And you can see here, he needed, all these transistors take physical area. And if we took that ASIC that was previously off processor and on an adapter card, we bring him onto the processor chip, we need to give him a home. And his home took 1.5 engines of real estate. So that's why we have 10 level 2s, but still only 8 cores. Okay. And before I go to the one at the right, I'll also point out in the bottom left, this AI, artificial intelligence unit. So we have a slide on that coming up. So again, red box for consistency with the previous couple slides, denoting the CP chip boundary. And then over here at the right is a zoom in again, where we took our same color coded CP chips, example, and then showed how the other 7 chips on the drawer facilitate the virtual level 4 for the drawer level for that reference core and that reference chip. And you see like all the gray lines showing again how everything is cross interconnected. Okay. Refresh on the history of topology changes, going all the way back to Z990, where we had these 4 books on these MCMs and each one is interconnected with it's what we call a ring interconnection, which is nice, except if you are in the upper left and you want to get down to the lower right book, you have to make 2 hops. Well, Z10 fixed this by putting a cross in the middle. So now, no matter where you are, every other book is exactly 1 hop away. And these buses are gold colored because they are, what I just tongue-in-cheekly call it the gold standard. These were custom manufactured silicon on glass technology, hardware implements designed and manufactured in East Fishkill. However, the world moved away from silicon on glass technology, and IBM Z was literally the last ones keeping the lights on at East Fishkill, and thus, having nobody else to share the cost, it became untenable to pass those costs directly on to all of our clients. So starting with Z13, we went to these purple buses just to have a different color than gold, but they're more industry standard interconnect and not as fine-tuned custom. And you can also see that drawers became what we previously called a book has now become a drawer. And starting on Z13, and Z13 was hopefully unique until the end of days in this regard, we split each drawer into two physical nodes, where each node had its own level 4 cache. This got a little dicey because, previously, like down here, like on Z12, anyway from Z10 to Z12, you basically had two latencies. You either hit on your local book or you hit on the remote book. And so fast latency for local book and a slightly less fast latency for the remote. You go up to Z13 and it's like, okay, well, you can now hit in your local node if you're in the left side of this upper left drawer. You can hit in the opposite node on the same drawer, and that has a latency that's worse than your local. Or you can hit on the same side node on another drawer, which has a different latency still. And then you can also hit on the opposite side node on another drawer. So now you got 4 different latencies, starting with Z13 on these slower interconnected buses. So this, and this was also amidst the first generation where we dialed the clock frequency back, and we had to rely very heavily on microarchitectural improvements that didn't benefit all workloads uniformly. So yeah, Z13 was a bit of an interesting machine in that regard. So going to Z14, you can see, looking leftward, we got rid of the double, this notion of 2 level 4s per drawer. We're now back to a single level 4 per drawer. We still have this loose association of clusters, where clusters are, I guess, amalgamations of CP chips that vary over the generations. But there is still 1 level 4 per drawer, and that allowed a return to a more standard ring cross point-to-point configuration, which got us down pretty much from 4 different latencies back down to the 2. And then in the upper right, Z15 really looks exactly like Z14, except we inserted another drawer into the structure. So the cross ring became a star ring. And then finally in the lower right, both Z16 and Z17 strongly resemble Z14, as we're back to 4 drawer boxes. But instead of having 2 clusters per drawer, we have 4 DCMs per drawer. So you got, I don't know, it's probably like 20 plus years of Z topology on one slide. The offering space. So the model number is 9175. We're calling the water-cooled IBM Z the ME1. We're calling the corresponding Linux 1 Emperor the ML1. And the Z models are, again, the subcaps can only support up to 43. So 400 through 443, 501 through 543, 601 through 643. And the full speed can support up to 208 engines, where our alphanumeric decimal encoding of 208 is K8. And just a table here showing the offering features for Z16 and row by row against the Z17 analogs or counterparts. It's all pretty straightforward. The first 4 are standard drawers. The max 39 can now grow to a max 43. max 82 to max 90, max 125 to max 136, and max 168 to max 183. The maximum 200 grows to a maximum 208. Okay, but these last two are both 4 drawers. It's just the standard 4 drawer and the maximum 4 drawer config. If you look at the columns, they all follow suit from the max feature, with one notable exception, the SAPs. We used to have this option where you could purchase up to 8 additional SAPs beyond what came with the box. It was never quite clear to me why this became a thing. Maybe it made sense in the long ago, but lately, this is one of these features nobody has taken us up on. And even if they did, they asked, well, what metrics would we look at to determine if we needed SAPs? I asked around and I found out what those were. I don't have them committed to memory offhand right now, but I just remember the handful of times that clients asked for it and they didn't see anything that would have motivated them to get more SAPs. So all that to say, the extra SAPs it's just an unnecessary complication of the offering space. So in an effort to simplify life, we dropped that going into Z17, and frankly, we don't think anybody will miss it. And then the final part of this graph, arguably the most interesting part, is out here at the right. So again, we're counting the number of drawers, 1, 2, 3, 4 standard configuration, and then the large configuration 4 drawer make up the 5 rows. You take the max feature defined over here at the far left, you divide that quantity by the number of drawers, you get average engines per drawer. And you can see, like on the Z16, the standard drawer size was about 41 engines, and then it jumped up to 50 for the large. Do the same thing for Z17. The average standard drawer is somewhere around 44, 45 engines, and then the maximum jumps up to 52. Okay. Well, then how does that correspond to effective capacity per drawer? Well, I just went to the multi-image LSPR table and picked off a Z16 739, which has a MIPS rating of 57,735. Did the same thing for the 741. Took a weighted average to do the 41.67 to get the 6724, et cetera, and for both generations. And then this final lower right column simply divides each element by its respective element. And so that's why you see up here the first 4, reflecting the standard drawers, grew by about 20%. And the large drawer grew by about 15%. It's 15.5. You could argue it actually rounds up to 16, but when it comes to quoting numbers, we tend to play it conservative. We just truncate. So we're calling this 15.5% just 15%. But hopefully you'll get a little more juice than we advertise. This is mostly a refresher that this is the AIU. As I showed on that CAD drawing, here's a simplified kind of like just a PowerPoint drawing, but you can see this upper right chip is very similar to the CAD drawing, and with the AIU in the lower right. And then here's a blow up of that AIU. And really all it is this 8x8 matrix multiply and convolution unit. And there's actually 2 of them. It's this layer, and then there's a second layer. So you can do 8x8x2 processing in hardware. If you didn't have the AIU, you could still do all the same functions. It's just you have to do all these vector-based operations with discrete vector instructions on the processors themselves, and then you have to aggregate the vectors into matrices and do all your partial vector-based manipulation and aggregate the matrix results. Whereas with the hardware, now you can just load the matrices of tensors directly into the AIU and process natively in hardware. So that allows much faster turnaround with hardware-based action instead of aggregated software based action. And this all gets into fundamentally, like, you use your credit card and there's fraud detection going on. There's once the detection starts, there's a clock starts ticking away, and if whatever reason, trying to access that data and do all these vector-based operations and try and determine if there's some fraudulent activity going on, well, if it comes in time, then yeah, you'll get the thumbs up or the thumbs down. But there are many cases where the machines just couldn't do it in time, so it times out, and so you waited for nothing. We threw all that work away, and we just crossed our fingers that it wasn't a fraudulent transaction. And hopefully with this AIU, and even more so with the Spire cards on Z17, the rapid acceleration of doing this in hardware should prevent a lot more of those timeouts and lead to much better results. So that's the idea behind it. It operates on these tensors. You have to convert the tensors into a format that can be used natively with the AIU. The AIU has its own direct memory access wiring built in, so it doesn't like all the cores can access the AIU, but once they set it up with their tensors or pointers to the tensors, the AIU can stream tensors directly from memory without having to rifle through the cores. So it's very efficient. Have the initial set of Z16 transformations supported by the AIU listed there in the bottom right. Z17 adds more. It also has support for 8-bit integer support in the matrix multiplication operation. Yeah, that's the recap and a few words about what Z17 does to improve upon it. Again, as I mentioned earlier, the AI, like a single AIU in isolation, operates much more quickly due to it being a second generation. And then the AIUs can also hive or distribute the work to other underutilized AIUs to clear log jams and queues when one AIU is getting beat up more so than the others. So all good things, and hopefully you'll be able to make use of this. Variability among workloads. This is a slide that went in on Z13 when we took the clock frequency hit and we had to make up for and we still had a 10% machine despite being like 9% slower. So we had to have 20% about in microarchitectural enhancements, and not all workloads responded uniformly to those 20% enhancements. So there was variability now where some workloads really liked the changes, some workloads didn't. The LSPR on the average typically held, but it led to some, I guess, consternation and some of the workloads that suffered. So that's just a function of Moore's law and hitting the power frequency barrier. And gone are the days of jumping from 1.7 gigahertz to 4.4 like we did on Z10 back in the day. These 30 or 40 or greater percent increases in frequency. We've been swizzling around between 5.0 and 5.5 for over the past 10 years now. And that's unlikely to ever change again. But all that being said, we expect migrations onto Z16 from previous generations to be stable. As I mentioned, the cross-drawer penalty is higher on Z16 and Z17. So try not to have massive partitions that don't fit within a drawer, such that some of their engines are on another drawer. You may actually run negative when you do that. It might behoove you to just cut the partition smaller so that it fits. And even without that added capacity, it's still probably better than having additional capacity that's cross-drawer and can impact you negatively. And just as a technical, thing that I would be remiss not to say, we have these massive level 2s now, like 32 megabytes, and previously 36 or previously 32 megabytes on Z16, now 36 megabytes on Z17. But back in Z15, they were like, you know, four, 4 megabyte I and 4 megabyte D, so 8 total. Now you're up to like over 4 times that. Um, it's possible that you could have some benchmark in many cases. It's typically not a real workload, but some clients love to run benchmarks. And so now if you had a benchmark that used to exercise the memory, but now given how large the level 2 is, it fits in the level 2 and doesn't make use of the larger shared memory, well, then it may run worse relative to Z15. Because you're not getting any benefit out of the shared cache growth. So like I said, I put that in writing just in case it happens, but I actually haven't had any clients complain about that on Z16. So I think it's just an academic point. All right, I'm a minute over, but this is my last real slide. I threw this in there because capacity planners are having pressures today that they didn't have historically, just given the rate of change in the working environment. It's like you got all these young kids coming in and they build out code and maybe it's not vetted and tested as well as it could have been, and it starts, maybe it wasn't efficiently written, so it starts consuming more MIPS than somebody more senior who estimated that consumption might have expected. That's just a generational disconnect, and that gap will close with experience. But nonetheless, the old guard is retiring, and the young guard just doesn't have that experience. New function adoption, right? Putting more of this stuff on the web. It was one thing when you had to go down to a bank branch office and stand in line and meet with the teller to figure out what your balance is, and now you can just do it from your phone whenever you want. And every time somebody does that, it triggers consumption. And it's like, well, maybe you don't have a good feel for when your system goes online, just how much clients are going to take advantage of that. So that's tough to plan for. Kind of related to the inefficient coding, you can have an inefficient web interface that isn't clear, and so the user isn't sure what the right link is they should click on, so they start bouncing around, and then that generates increased consumption that isn't necessary. Oh yeah, and your consumption overall per tran might be increasing, but not the trans themselves, like the quantity of trans. This is just because new standards get rolled out, either mandated or self-imposed, where trying to avoid security breaches. So there's higher degrees of encryption and redundancy and fraud detection built in. So your existing transactions become more, they have greater heft. And that too is difficult to gauge years ahead of time when you're buying a machine that you're going to hang on to for several years. So all of which is, increasingly converging in real time these days. So just not sure what you can do with that other than try your best to keep these things in mind. If you can think of other things I don't have on this list that you think should be here, by all means, shoot me a note and I'll improve the list. And then, yeah,
Dave,
my final, go ahead.
Sorry. We have a question in the chat. Asking uncommon super low nest intensive workloads that fit in the L2 on Z15 may run worse on Z16/Z17. Could you please elaborate more on this? Also, how would it be Z16 versus Z17?
Yeah. Okay. Well, this is my final slide. All it does is show, pertinent bullets from the previous deck with like a parting thought. So that's all I'll say about it. Yeah, to the question, let me go back to the actual wording. Yeah, this bottom bullet down here, uncommon super low nest that fit in the L2. Yeah. So fitting into the L2 means like, well, if you miss the level 1, you have, well, John Berg's presentation from the Washington Systems Center, he's got all those CPU-MF formulae that show how you can compute the level 1 miss percentage, which is really a level 1 miss rate because it's relative to 100 instructions. And then each one of those misses has got to hit somewhere. And so there's a formula to tell you how many are going to hit, or how many hit in the level 2, how many hit in the level 3, how many hit in the level 4, local and remote, and then how many hit in memory. And you expect to see like a uniform, depending on the machine generation, how big those caches are. We expect to see, like Z15 might have seen 75% of all level 1 misses resolve in the level 2, and then like another 10% resolve in the level 3, and then maybe 5 or so with the level 4, and another percent or 2 in memory. Well, that changes significantly on Z16, where it might be more like 88 to 90% of the misses are going to resolve in the level 2 because it's 4 times as big, and then maybe 5 to 6% hit in the level 3, so on and so forth. Well, if you were running some benchmark that just, maybe it's doing pointer chasing, or who knows what your benchmark of interest is doing, but it could be that it's just almost all the level 1 misses are resolving in the level 2 on Z15. So it doesn't fit that 75% of typical workloads, like real online workloads, running production stuff. It's an artificial benchmark that has a different characteristic, and maybe it's hitting 95% of the time in the level 2. Well, if you take that same benchmark and you run it on the Z16 that has even 4 times bigger level 2s, it's going to do the same thing. It's going to hit like 90 to 95% of the time in the Z16 level 2 as well. So there's going to be no benefit realized at all from the larger shared caches that you're not going to utilize with this tailored benchmark. The LSPR ratings, like that 11%, counts on you making use of the shared cache in a normal way. So it's just a statement about benchmarks that might do wacky things that don't fit the normal profile, beating up incredibly on the level 2 cache and not getting any outside or outer layer of shared cache benefit. If that wasn't clear, I know it's because I know I'm over, but feel free to reach out to me, and there's my email address. We can talk more about it. But that's the idea behind that statement. Was there another question in there?
Nope, that was the only one.
Okay. I didn't know if that was like part of me thought it might be a 2-parter.
Nope, that was it.
All right. Well, if there's nothing else, I very much appreciate everybody coming here. Here's this is session 5I, and there's the link, there's the QR code, and hopefully you'll think favorably when you click on those those ratings. Very much appreciate it, and again, thanks so much for coming.
All right. Thank you, everybody. As Dave said, remember to submit your feedback, session 5I. Sorry for running over, but all good information, and enjoy the rest of your day. Thank you, Dave.
Yep. Thank you. Take care. Bye-bye.
You too.